let's welcome Kaie Kubjas for her last lecture.
Yeah. So I wanted to make some remarks about yesterday. So there was a question about reference for real algebraic geometry. So one book I recommend is the Roy Real Algebraic Geometry. Then there was a question about the rank nullity theorem. I was thinking about it. I don't know anything similar for a non-negative rank, so it doesn't mean there isn't, but I'm not aware of it. And then for those, so there was this mistake that I made. Anyone who wants to discuss, we can discuss it after the lecture, but I don't want to spend any more time on this. Okay, so these were the 3 comments. So today we will combine many things that we have seen. So we will talk about boundaries and semi-algebraic descriptions for non-negative factorizations. So let's start with some notation. So we denote the set of m times n matrices of non-negative rank at most R. So because this will be the set we are interested in. And we use this calligraphic M notation. So M times N and R denotes the non-negative rank. And you might ask why here is at most R and not exactly R. This is to make things simpler. And I will do an example for varieties of matrices of rank at most R. There we also consider we have this at most. So one can get rid of this, but then it just like adds a little bit more, make things a little bit more complicated. Okay, and the goal is we want to find a characterization of this set. Then I will explain what I mean by this. So that if you're given an M times N matrix, this characterization allows us easily to check if it has non-negative rank at most R. Okay? Because this definition, like this is just non-negative rank at most R, but I will discuss it. Like so far, we don't have an easy way to actually check if non-negative rank is at most R.
What do you mean by factorization of this set?
I will explain. Hopefully, it will become more clear in 5 minutes. So that and maybe let me add algebraic to make it, because it's true we talked about geometric characterization, but maybe we want to find something still simpler or something that's easier to check. So characterization allows us to easily check whether the matrix is in this set. And now my question, so I'll give you 20 seconds to finish writing. So you don't have to write down the questions. So what is such a, like, what this characterization could mean for matrices that rank at most R? What would be an algebraic characterization? And this is a question to the audience. So if I give you an m times n matrix, I ask, for example, is the rank of this matrix at most 3?
Minus.
Exactly. So you can check the whether all the 4x4 minors of this matrix vanish, right? This is an algebraic, and that's why it's an algebraic prior. I said before I want at most R, so this is the reason. If you check 4x4 minors, it doesn't say that the rank is exactly 3. It says the rank is at most 3. Okay. So the answer is that in this case, this is a variety such that all R plus 1 minors are 0. Okay. So now going back to the matrices of non-negative rank at most R, what kind of characterization are we? So this is going back to Dr. Imran's question, what's this characterization that we are looking for? Are we looking something similar? This is like given by equalities, or can we, is it like semi-algebraic set, or what is it, right? And so now we'll make connection with yesterday's lecture. So consider the map. Phi from R to the n times R times our Cartesian product with R to the R times n to R to the n times n that maps matrices A and B to their product. So this is a map where each coordinate is given by a polynomial. And then if you consider this set, the set of matrices of non-negative rank at most R, it is the image under this map of the non-negative ordinates. in this sets, right? So is the image under phi of the set of matrices, matrix pairs A and B, such that A and B are both non-negative. So, and this is a semi-algebraic set. In fact, it's in a polyhedra cone, but so we are interested that it's an algebraic set. And this is a polynomial map. So now we can apply the theorem from yesterday that said that the image of a semi-algebraic set under a polynomial map is a semi-algebraic set. So now it becomes, so now I can say more precisely what I mean by this characterization. What I meant is semi-algebraic description, right? Because now we know that this MR is a semi-algebraic set. And you might ask, okay, but we already have, so I haven't written down here, but we can write, M is equal to A times B, where A and B are non-negative. But this is not an explicit description, meaning that if I give you an M, you would first have to find this A and B that verify that M is has non-negative rank at most R. But I'm asking a description that doesn't involve A and B. I'm asking for this description only in terms of the entries of M. So in the same way as we have description for matrices of rank at most R. Okay.
Words, how this B is a semi-algebraic set.
Sorry?
How is this B a semi-algebraic set?
So B is a semi-algebraic set because it's just given by linear inequality. So you can also consider it, if it's confusing, it's in M times R plus R times N, and we are given by linear inequality, like it's characterized by linear inequalities. So if you remember yesterday, there were the sets S and T. So the set S is empty. So the S was the set of equalities, and the set T are precisely given by each each variable is in the set T. Exactly. So this is really the non-negative ordinate in the in this R M times R plus R times M.
XIJ जो है ना वो कोऑर्डिनेटेड है. अगर आप पहले के XIJ ले रहे हैं दूसरे के Y के ले रहे हैं XIJ is 0 and 5 here.
So in yesterday's notation, S is
Set of
S and T can only have polynomials. Yes, but S is empty set in this case because S was the set of polynomial equations, and T is the set of polynomial inequalities. But we don't have equations; we have just inequalities.
It's like linear point.
These are linear. Linear is like special case, so it's actually even simpler, right? So that's why I said this is actually polyhedral cone, and every polyhedral cone is also a semi-algebraic set. Okay, so and that we're all on the same page. If you thought about the homework or like exercises yesterday, but even without that, my question to you is find the semi-algebraic descriptions of M1, M times N, and M2, N times N. So the two special cases when we consider the non-negative rank at most 1 and non-negative rank at most 2. So I'm claiming that you can answer these questions. So does anyone have suggestions? What would be semi-algebraic descriptions for M1 and M2? So why I might ask for 1 and 2, what was special about 1 and 2? Does anyone remember? Was there anything special about? Exactly, so the rank and non-negative rank are equal, right? So, can you say it again?
The same description.
Almost.
Almost.
Almost, there is something else. Is the non-negative rank defined for matrices that have negative entries? No, right? So we need extra the condition that every entry is non-negative. So, but it's this characterization with this condition that every entry is non-negative. Okay, so we use that. If M is non-negative and rank of M is 1 or 2, then non-negative rank of M is equal to rank of M. And hence, for R1 or 2, so this M R M N is equal to all the M times N matrices such that M is non-negative and R plus 1 minors of M vanish. Unfortunately, these are the only simple cases. And so this is the difference. That
we are considering who are already positive.
do you mean difference with this one or this one? Yeah. So well, here the difference is that we have written. So let's say this is not explicit. So if I give you a matrix M, you know this is it doesn't. It tells you have to find this A and B. Whereas here you can just plug in to this all of these constraints and then check if it satisfies the conditions.
And so basically this describes it as a semi-algebraic set.
It describes it as a semi-algebraic set. Exactly. And you know, this is an efficient way actually checking the non-negative, or okay, it's not checking the non-negative rank, but checking whether the non-negative rank is at most true. Unfortunately, from here on, the things get complicated. And for some reason, for the non-negative rank, it's often the case that non-negative rank 1 is trivial. Non-negative rank 2 is often easy as well. And from non-negative rank 3, things get complicated. And from non-negative rank 4, things get really complicated. So this is often, you know, how the results are for non-negative factorizations. And so the only next case that's known is non-negative rank 3, like the semi-algebraic description, and I'm going to talk about that now. And to derive, and I'm going to talk about paper together with Elina Roba and Per Stürpels. We can derive this. Derive the semi-algebraic description for non-negative rank at most 3. And this derivation relies on lecture 2. Remember, we talked about this polyhedral geometry. So this is the reason why we needed to talk about it. And I'm going to actually use another simplification of this polyhedral characterizations. So I'm not going to I'm going to skip one step. So a matrix of rank 3 let me write a non-negative matrix. A non-negative matrix of rank 3 gives 2 polygons. And this is something that I also mentioned when we proved, or had the proof idea for the that if a matrix has rank 2, then it has non-negative rank 2. That if a matrix has rank K, then actually the 2 polytopes nested in each other can be taken as K-1 dimensional polytopes. And in this case, the rank is 3. And polygons are 2-dimensional polytopes. And so this was the geometric characterization. The matrix has also non-negative rank 3. If and only if there is a triangle nested between B and 2. Triangle delta nested B. So what I wrote down is what we discussed on Wednesday, but it's another version of what so I didn't explicitly write it down in the way that I'm writing right now. But recall that checking whether a matrix has non-negative rank at most R was equivalent checking if there is like a polytope with R vertices in between 2 polytopes. So recall we are like situation, we have 2 polygons, and we would like to know is there a triangle in between them. Almost. Okay, And so what we did, and I'm not going to talk about the logical order, I'm first going to talk about the semi-algebraic description, although I'm not going to give it explicitly. So we came up with an algorithm checking whether there is a triangle between two polygons that can be translated to a semi-algebraic description. And there is an algorithm before from 1989. There is an algorithm by Agrawal et al. For checking whether there is a triangle between two polygons. But this we couldn't figure out how to translate the semi-algebraic description. So we came up with another algorithm. So an algorithm for checking
P and Q are determined by the matrices which are varied in the decomposition, right?
Yes, but not in a so they are actually determined already. Yes, that's true. But actually, what I didn't tell about, one can get them not from the non-negative decomposition. One can get them already like from any decomposition. Yeah, but the way how I talked about it, that was from non-negative decomposition. But there is like another way to get them without being using the non-negative decomposition.
How do they determine this triangle? So the triangle is the vertices of the triangle is determined by.
Well, we want to find the triangle. So it's I'm going to tell you how. So the triangle is not given. So the triangle is not given. But actually, sorry, I said something wrong. So also the way how I described how to get the polytopes P and Q, they didn't require the decomposition. So remember the triangle corresponded to the cone of W. So we just need our matrix X gives the two polytopes. And as long as X has non-negative entries, the two polytopes are nested inside one another. Okay, so an algorithm for checking whether there is a triangle nested between two polygons. Yeah, so maybe let me emphasize it once again. We had this nested cones or polytopes problem. We are given two polytopes and we want to find this in between. So now I'm like giving an algorithm in this very special case how to answer this question, how to find this in between triangle. Okay. So let me explain the algorithm. So the algorithm consists of two parts. So first is the inner one is P and the outer one is Q. And the first one is for every vertex of Q, check. So now I'm going to draw instead of writing. So fix a vertex of Q, then draw the supporting lines. So the most extremal lines when taking into account the inner polytop P. Then see where it intersects the boundary, take the intersection points, and then connect the intersection points and check if P is contained in the resulting triangle. So in this case, you see it's not the case. So one has to repeat it for all the vertices of Q. So I did for one vertex. Now, I didn't find a good triangle. So let's do it for another one. I still didn't get a good triangle, and I repeat it for every vertex. So if we find one triangle, we are done. If not, then we continue to the second part. So
sorry, so you take a line, start with a vertex, and then you're supposed to catch a vertex with the polygon inside.
Exactly, and I think you can take it for every vertex, but I want to take supporting lines to P, meaning that P is completely on one side of this line.
So you don't necessarily have to touch the vertex of P.
I do have to touch, so
because you want a supporting line.
I want supporting line, but the supporting line, in fact, will always touch a vertex. Yeah. So this was the first part, where we go over all the vertices of Q. And in the second part, for every edge of P, check. So now I select an edge of the inner polytope and I extend it to the boundary of Q. I find these 2 points and I find supporting lines from these 2 points to P, meaning this one and this one, and I extend those lines until they intersect, and I check if this intersection point is inside the polygon. So here again, that wasn't good. So I actually don't know if in this, let's try something where there is hope. Maybe this one, but probably there isn't in this case. I suspect. See, they again intersect outside the polygon, and it follows. So it follows from the results of Mons, Smith, and Weisbrot. That if there is no triangle of the form like in 1 or 2, then there is no triangle at all between P and Q. So it's actually, although there could be infinitely many triangles that we have to check, this is saying there is only like finitely many. We only have to check the number of vertices of Q plus the number of edges of the number of possible triangles.
What do they use to do this?
Well, they don't. So the algorithm is ours. They study critical configurations between two polygons, and they study what happens if you have a triangle in between two polygons, and if you try to rotate, like epsilon, like changes in the triangles. So, but actually, what they in their paper they do, like their main goal is to study the space of non-negative rank 3 factorizations, meaning that they fix a matrix M, and they want to study the space of all the factorizations A and B of a particular non-negative rank 3 between for a matrix M. So they don't have the algorithm, but they, let's say, it's about the topology of the factorizations that we can use. Some of like their results about critical configurations.
Yeah, and the polygons don't have to be regular.
No, it's any polygons. Yeah, as long as they're one is inside the other.
And you can say something about why the existence of this triangle, what it has to do with this characterizing rank.
So I'm going to write down one sentence. Okay. Unfortunately, so let me write down this one sentence and so this algorithm gives the semi-algebraic description of M3 using the Grassmannian-Kaie algebra. And this is how I'm going to comment on it a little bit. Unfortunately, I can't really say anything more because that would probably be at least one lecture explaining how to get this semi-algebraic description. And it's not like it's a nice semi-algebraic description. We talked about basic semi-algebraic sets and semi-algebraic sets and how we wrote it. I now forgot that I think it was as a union of 400 basic semi-algebraic. So it's not something that I didn't write the semi-algebraic set on the blackboard. Okay, so I said that unfortunately I won't be able to say more on this, but let me comment let me wait till everyone stops writing. So basically, the main idea is there is like another way how to get this geometric description, and for a rank 3 matrix, and then the rows of this W matrix, they are interpreted as lines in the projective space B2. And the columns are represented as points, and they correspond to these lines of P and the points of Q over here. And then we have like we have operations defined as cross products that correspond to intersection of two lines and the span of 2 points. And then using this Krasvenian-Kaie algebra, and this that the elements are lines and points, and we have this operations. This algorithm can be translated to a semi-algebraic description. So, but it's really like something that would take me at least, let's say, one lecture to explain how to do this translation. But the main idea is, the points of P correspond to the rows of this factor. Columns of this factor correspond to the points of Q correspond to the rows, and the edges of P correspond to the columns. But yeah, so it's so you see, to get the semi-algebraic description for M3, it's already quite a lot of work. And so we talked about open problems yesterday. So M4 is completely open, but I don't know if this is a problem I would recommend you to work on, because I think it might be just very hard. But I think even like partial progress would be nice.
They try. Apparently, on loop side, look at this particular result. One can think of the case of M4 something.
Yeah.
It's going to be 4 vectors something.
So basically, I think it would be enough to come up with an algorithm checking whether there is a tetrahedron in between 2 3-dimensional polytopes, or like at least if. But as far as I know, there is even like there are partial results, but to my knowledge, there are no complete results. Checking whether there is a tetrahedron between 2 3-dimensional polytopes. So let's say, but that's why I said like maybe one could come up with some like partial results. One could get like relaxations of the semi-algebraic description could be also very interesting. Yeah, but I mean, how I would approach it, because I don't know any other way, would be considering tetrahedron. So that might be a nice problem. Let's say I don't recommend maybe to attack the M4 directly, but if anyone wants to think about nesting tetrahedron between 3-dimensional polytopes, that might be a nice problem. But I think it's still a very hard problem. But to have partial results. Okay. And now I'm going to write a corollary, and actually this is not the direction. So actually in the paper, what comes now as a corollary comes first, and then we use that to obtain this algorithm. So we talked about algebraic boundaries yesterday. So a rank 3 matrix M is on the boundary of M3 if and only it contains a 0. So if a matrix contains a 0, it's always on the boundary, because if we change the 0 to a negative number, then we get something that's not in the semi-algebraic set. Or all triangles that can be nested between P and Q are of the form let's see. Now it's a little bit. So let me explain what have I drawn here. So both of these configurations have 6 incidence relations. So if you look at the triangle, then all its vertices have to be on the boundary of Q, and all the vertices of the inner polytope P, sorry, not all the vertices, every edge of the triangle needs to contain a vertex of the inner polytope. And moreover, I have circled this number 1 here. Actually, one vertex of the triangle needs to coincide with the vertex of the outer polygon. So we have actually 7 incidence relations, because I'm going to count this as a double incidence relation. So this vertex is really on 2 different edges. Okay. And the second configuration is almost the same. Every vertex of the triangle is on the boundary of Q, and every edge of the triangle contains a vertex of P, and moreover, an edge of P lies on the edge of the triangle. So this is my double incidence right now. So in both cases, we have 7 incidence relations. Yeah, and as I said, there was yesterday one question like, why would we care about algebraic boundaries or boundaries if we want semi-algebraic description? The reason is actually like, although I wrote one Smith, one Stratton there, and I'm writing it in the other direction, but actually we first find algebraic boundaries, then boundaries, and then semi-algebraic descriptions. So it's just like a tool, right? So actually, like these results are this like critical configurations from one Smith, one Stratton. So let me write down something. So I understand right now, so you should see now I'm more writing down results, and I don't expect that you understand why it follows necessarily from the previous results that I've told you. So another, let's say, fun fact is that every incidence over here corresponds to a 0 in a non-negative factorization. It might be surprising, but so it turns out, you know, if you have this kind of triangle nested between 2 polygons, then the corresponding non-negative factorization will have 7 zeros.
I don't understand what you mean by it contains a 0.
I will write it down. So if we have a picture like this, then corresponding non-negative factorization will be of this form. Or the the transpose of this configuration. So, bulk configurations.
Incidents.
So how one can think about it. So let me, and that's why I actually labeled there. So if you think of these, so let's say, if you think of this as the columns as the vertices of the triangle, and you think, and I think the rows now correspond to, but I haven't drawn, this is 4 edges, 1, 2, 3. I haven't drawn, so this would actually have one more row. And this just means that the first vertex, so if these are like edges of Q, right? So I have a 0 if the vertex lies at the corresponding edge. And the same here, you can think of it, and I think the edges of the triangle. And you have a 0 if the corresponding vertex of the inner polytope lies on the corresponding edge of the triangle. So this is, and how to show it is to show that these geometric characterizations that we define, they come from 2 different ways. So one would have to show that these 2 ways give like equivalent geometric characterizations, and in the other way, it becomes quite like, at least to me, this other way, it's easier to show this the zeros. But again, this is like, it's definitely not immediate from what we have discussed. And maybe a question. So yesterday we talked about the boundaries of a polynomial image, and the boundaries there are 2 types. One type that comes from the boundaries of the, the semi-algebraic set that we start doing, and then we have boundaries that come from folding. In this case, what type of boundaries do we have? So we have only the boundaries that come from the boundaries of our, the pre-image, because the boundaries of the pre-image are given some coordinate is equal to 0. And we see that if you get something on the boundary, then it comes from a factorization that is 0. So we don't have to, in this case, we don't have to worry about this folding at all. So we already get all the boundaries from the zeros. But we didn't use this to actually compute, the boundaries. We used this geometric characterization, but an observation that can be made that the folding is, if it gives something, then it gives something that's already given by the zeros in the factorization. Okay, so in the last 5 minutes, so that was, let's say, the pure mathematics part to me of these non-negative factorizations, and this deriving the semi-algebraic descriptions and boundaries. And it turns out there is this really surprising connection with that applied part that we started with, that non-negative factorizations are used in data analysis. So So let me just very quickly mention a couple of things about it. So in particular, a very hot topic in this data needs part is uniqueness of non-negative factorizations. So for many of the applications, it's desirable that there exists a unique non-negative matrix factorization, and I will say what it means, because it doesn't actually mean unique. So for many of the applications, it is desirable that there exists a unique non-negative matrix factorization. And why it's important? It's because this factorization, they mean like they correspond to the parameters of the model, and this means we have like identifiability, or we have unique parameters that give our matrix. So this is really important. But actually, the non-negative matrix factorizations are never unique. So if you have non-negative factorization A and B of a matrix M, then also this will be a non-negative factorization where C is a permutation matrix or a diagonal matrix with non-negative entries, sorry, positive entries. So, or positive scaling matrix. So when I say unique, I mean unique up to up to scaling by a permutation matrix or a positive scaling matrix. And let's see, last thing that I will write down is that when a matrix lies on the relative interior of the set MR n times n, then M is not uniquely decomposable in the non-negative matrix factorization sense. And hence a necessary but not sufficient condition for M in MR to have a unique decomposition. Is to be on the boundary of MR. And using this observation that a necessary condition for uniqueness is to be on the boundary, together with Robert Krohn, we derived so far the best known necessary condition for uniqueness of non-negative factorizations for any R, so not only for non-negative rank 3. So, and this condition uses only its combinatorics plus linear algebra. So, and that's why I really like this topic. Like, eventually, you know, we get results that applied people are interested in, but in my opinion, you know, like without knowing these tools from algebra, polyhedral geometry, you know, it's not possible to come up with this result. So, like, it's really how pure and applied mathematics come together. So, yes. So it means that there is only one factorization up to, you know, we are allowed to get the factorizations up to that we get that are of this form, where C is a permutation matrix or a diagonal matrix with positive entries, but that there are no other factorizations. So this is what it means, uniqueness. Sorry?
It is not that there are more than one decomposition.
Exactly.
The question is that there is more than one way to decompose. So is there any effect of the diagonals more than
well, so we assume, like, once we fix non-negative rank, it can be both. So it doesn't have effect on the non-negative rank. So let's say I fix non-negative rank 4. There are matrices that have a unique factorization. There are matrices that have finitely many factorizations. There are matrices that are that have infinitely many factorizations. So just by knowing whether there is a unique decomposition or not doesn't say anything about non-negative rank of the matrix. And maybe one more comment that I want to say. So here I wrote, but not sufficient. In the non-negative rank 3 case, it is necessary and sufficient. So non-negative rank 3 case is much nicer, and that's, I think, one of the reasons why we can understand it better. And you know, yes.
More than one decomposition, like decomposition. So in data analysis problems, so is there any trick to use one or the other one?
So you can't really distinguish between them, and that's one of the reasons why uniqueness is so desirable. Let's say, you know, you take this decomposition of PHs, and you have several factorizations. Then it's not clear, you know, what would give better explanation, like what are the better basis images for your database. Maybe, you know, once when you look at them and you can say something, but in general, it's not known if one is better or another. And so that's one of the reasons also why uniqueness is so desirable.
Okay, are there any other questions by the audience? Okay. Yeah.
Sorry, I it's like magic and stuff like the plus one Kaie and Algebraic. So you said that you draw that picture of the decomposition of X on the right. You said that the rows correspond to vertices.
So
are the two things related to the picture that you've drawn for this one here?
So this is related to this one, and maybe I got it. I'm not completely sure that if I got it correct, but so the columns will always correspond to either vertices or edges of the triangle, because the numbers have to match exactly. And so actually here, if I wanted to be completely correct, I should have added one more row, because there are 5 edges. But and you know, I'm probably mixing up. Maybe it's the other way around. Maybe it's actually this configuration for the first one. So I always mix it up. But yeah, so this corresponds to the edges of Q, and this corresponds to the of B, but maybe, yeah. So maybe I'm like, and for the Crossmanian Kaie algebra, it would be the other way around, right? No, sorry, I think it's correct. Because for the Crossmanian Kaie algebra, so we're interested, for example, in the H spanned by two vertices of P. So that's why it's the vertices that we want. And then we apply an operation on the vertices of P to get a line through to the vertices. And this operation is actually cross product. So you take the vectors of these two vertices in P2, and then you do the cross product to get a line. And then basically what's like one more thing that's hidden there, so maybe it was over here, we want to check if a vertex is inside polytope. So that seems like, okay, how do you check that? And there you use this that determinant is positive or negative depending if something is like right hand triple or left hand triple. And so what one does is I think it was like you check this triple and you check this triple with one vertex of P, and you want to check if they have the same sign. So there's really lots of things going on there. But yeah, so I think here maybe it's actually even correct that these are the vertices of P and these are the edges of Q, because because for the and then we want to, for the first part of the algorithm, we looked at that. I think I have erased it, but we looked where we had a vertex of Q, and then we want the supporting line. Exactly. Yeah.
Any other question by the audience? Okay, just curious about what is the interest if we do study this particular problem for the square matrices case instead of taking the m cross n?
If you consider
the square n cross n.
So this is called completely positive rank. And actually in the paper with Robert Crone, we also addressed a completely positive rank case. But I think the semi-algebraic description for completely, so that might be actually open problem, let's say, and that might be not so difficult. I think in my, as far as I know, there is no semi-algebraic description for the completely positive rank in any setting. And so probably then completely positive rank tree case is something, is, using the tools from the non-negative rank. So let's say in the paper with Crone, we address the completely positive case. In the paper with Sturmfels and Rokava, we don't address the completely positive case. So that might be a really nice problem for a student to work on. And maybe if we go talk about open problems, one more thing that I would like to mention. So I talked about non-negative rank. So now completely positive rank was brought out. So Hamza Fabsi and Fata Brillo, they have this conic atomic rank. Maybe it's conic rank, maybe it's atomic rank. It's some combination of conic and atomic. So this is a rank that's defined when you have a cone K and you have a variety V, and your rank 1 matrices, according to this atomic rank, are the matrices that are in the intersection of A and B. And now the conic rank is defined as the smallest R, such that you can write your matrix as a sum of rank 1 matrices. And there is, so non-negative rank, completely positive rank, positive semi-definite rank, some sparse rank, are all special cases of this completely positive, of this conic rank. And the same questions can be asked for other conic ranks. And positive semi-definite rank is quite well studied. So there are like overview paper by Rekka Thomas, Pablo Carrillo, not Bench-Schultz, Jacques Correa. But I think and another, one also for the positive semi-definite rank, the semi-algebraic description is not known in any case to my knowledge. So I think, if you look into these conic ranks, and you look what's been done in non-negative for non-negative rank, and you can ask exactly the same questions for other conic rank. So these are like lots of open problems to work on. So let me just write down. So it's Hamza Fawzi and Parilla. And the paper, I think it starts something with self-scaled bounds, and I don't remember how it continues. I think that's the beginning. But I think if you already put those names in self-scaled bounds, then you'll probably find the paper. So lots of open problems to work on.
One question which is quite probably a naive or again thinking a little bit more louder. In the square matrices cases, we have the LU factorization. So one can do some modification by looking at the rank or to see the things through. Okay, LU factorization is very special one.
Yes, so then one considers symmetric factorizations for the completely positive. Okay, so I guess if you consider the square case, you can consider it a special case here. If you don't have symmetric matrices, the completely positive case is for symmetric matrices. And then you have like the factorization is A times A transposed. Yeah. And actually the results are, sorry, okay, I haven't written down any of the results here. I guess this is all semi-algebraic description. But for these boundaries, the results, they're quite similar for the non-negative rank case. So one can use, basically, you do the proofs for the non-negative rank case and you do almost the same proofs for the completely positive rank case. But yeah, so if you look at the paper, Krohn, Kubjas. So, and I also forgot the name. Maybe it's the uniqueness of non-negative matrix factorizations via rigidity theory. So there you can find more about this completely positive rank.
Okay, we are all done. Any question from the IBA side or from the audience? This is your last chance to ask the question from Kaie Kubjas. Okay, if this is the case, let's thank Professor Kubjas for her wonderful lecture series in this CIMPA School. Kaie, for coming all the way to Pakistan and giving such a wonderful area, introducing this wonderful area for the participant and for everyone here in this CIMPA School. Thank you very much.
Thank you very much, and I would really want to thank all of you for being such an active audience. It's been really a pleasure to teach here. So thank you very, very much. And I will be around all day if you want to have any questions or like just want to discuss. I'm very happy to talk to all of you. Thank you very, very much.
Thank you. It's time for tea.